Welcome to the special CosmoQuest Dawn Hangout. We are going to be talking about the largest asteroid and also known as dwarf planet Ceres. I am Nicole Gallucci. I am a postdoc with the CosmoQuest project, so I'll be checking your comments and running some tech while we do this hangout. And I have with me Brittany Schmidt. Hello. And Julie Castillo Roges. Sorry. So these are our two scientists who will be talking about the science behind Ceres.
Julie, are you there?
Yes.
There seems to be a delay.
All right, we're almost up. Oh, we're here.
Yay! Julie, can
Hi, everyone. Welcome to the special CosmoQuest Dawn Hangout. We are going to be talking about the large...
Oh, sorry. Okay, so Whitney, the sound's coming through your speakers. Sorry, Julie, I muted you. You can unmute yourself again. Sorry, we're having a little bit of tech difficulties. We also have Whitney Cobb from the Dawn mission. She is behind the Twitter feed, and she will be helping us answer your questions. So what's the Twitter handle? It's at NASA_Dawn. Okay, so we can't hear you right now.
Yeah,
sorry.
there you go, yeah.
Awesome. So she'll be answering your questions on Twitter. Some other ways that you can comment, ask questions is using the Google event page. So if you're watching on the Google event page, we're watching those comments already. So we see lots of hellos from Indy, from Norway. So hi, everybody.
Awesome.
And also, yeah, also the YouTube page. If you're watching this on YouTube, you can use that comment thread as well, and we will see those. Brittany, do you want to go ahead and get us started talking about Ceres and what we know about that dwarf planet already?
Yeah, sure. So I'm excited that everyone could come and listen to this, and if you're watching this after the fact, thanks a lot for being interested. So I'm one of the scientists that's involved with the Dawn mission. I'm actually on the education and public outreach team, and I'm coming to you from Atlanta, Georgia, actually for the first time. So that's kind of exciting. And we thought we'd have a discussion today about Ceres because it's the next target for the Dawn mission. So in the past couple of months, even the last year or so, we've been telling you a lot of information about Vesta, which is the first target that Dawn visited, spent about a year orbiting Vesta and doing great science there. And so where Dawn is at right now is actually kind of halfway between those asteroids. We're looking for arrival at Ceres in actually very early 2015, somewhere around March 2015. And what we wanted to do was to share with you why we're so interested in Ceres, especially alongside Vesta that we've just departed from. So I'm excited to tell you about Ceres because I think of Ceres actually as a game changer in the solar system. So in many cases, we visit classes of objects. We visit asteroids, we visit icy satellites, we visit gas giant planets, we've visited the terrestrial planets time and time again. What's really interesting about Ceres is that Ceres is arguably the only one of its kind. It's the innermost, potentially icy body, at least a major body. Ceres was discovered in the 1800s, actually, by German astronomers, and was originally designated a planet. It was actually so large, it was exactly where we expected it to be from the Titius-Bode law, which is an observational law, so people went looking for this missing planet. What they ended up finding was Ceres. We now know Ceres is the largest asteroid, or the earliest discovered dwarf planet, if you want to think about it that way. But Ceres is a really, really exciting object, and the reason for that is because of what we know and because of what's so surprising about it. So we think about asteroids, we think about dry objects, we think about little pieces of rock floating in space, and it turns out that Ceres is not like that at all. So I've got an image here actually showing Ceres alongside the other asteroids that we've visited with spacecraft. And just to give you kind of a sense, if Nicole throw that up. So this is an image of Ceres. And Ceres is that big round one in the middle. Ceres is almost 1,000 kilometers across. So if you're thinking about an asteroid, you're usually thinking about the things I'm showing to the right-hand side of that image. So if you look there, you've got Itokawa, you've got Matilda, you've got these asteroids, Anne Frank, that we've visited with spacecraft, and that's their actual size, with the exception actually of Itokawa. So Itokawa is the kind of the third one on the right-hand side, kind of little bent, kind of dusty-looking one. And Itokawa, that's actually about 5 times its actual size, that little tiny box that I'm showing right there. So that should give you kind of a perspective on why Ceres is so special. But if you look at Ceres more carefully, what you'll notice is that it's also totally a different shape than what you see, even with Vesta, even with this giant planet-sized asteroid that's the size of Arizona, right? That's how big Vesta is. And we saw that it was basically round. It had all of these planetary-type processes going on at its surface. But even if you look at Vesta, you'll notice that it even doesn't look as round as Ceres. So that's the first real indication that we had from direct imaging that Ceres was so special. We knew other things about Ceres beforehand, but basically it's the combination of this shape, its size, and its total mass that actually tells us that Ceres is incredibly low density, despite being almost a third of the mass of the asteroid belt. What that tells us is that underneath this kind of dusty, dirty, clay-type surface, we think that Ceres might actually be icy. So if you want to think about it, it's a little bit like a Europa or an Enceladus with a dusty layer on the outside. And it's the only object that we know of in the whole solar system that's like that.
Brittany, we have a question, I think, relating to that from Sylvan Westby. Has Dawn crossed the frost line?
Well, so that's actually a really interesting question. So the frost line, or the ice line, or you may have heard the snow line, is kind of a concept that astronomers and planetary scientists use to describe a concept that somewhere in the early solar system, there was a point at which water ice became stable, where when you're building a planet, instead of just sweeping up rocks, like mostly what the Earth and Mercury and Mars and Venus, mostly what they swept up to build themselves was solid material in the form of rock. Well, there's a certain position in the solar system where solids also start to include ice, where it got cold enough in the solar system for ice to start forming. And so basically at that point in time, you can start sweeping up rocks that are actually made of ice. And so we think that that's what's happened in the case of Ceres. So what's interesting is that as we learn about Ceres, if Ceres does in fact turn out to be icy underneath that dusty regolith, then that'll actually give us an idea of potentially where the ice line was in the early solar system. We don't actually know what that position was, and it probably changed in the early in the history of the solar system as planets were migrating around and as the sun was actually becoming more and more energetic. So we're not quite sure exactly where that frost line was, and so if we can actually confirm that Ceres is icy at 2.7 AU, then that actually gives us an idea of where that frost line might have been in the early solar system. So it's a really good question. That's actually one of the reasons that we're so interested in going to see Ceres, is because of that implication for what water was doing in the inner solar system. That's, of course, important because water is important for us, and it's very important for Ceres, which may be made of ice and potentially have had an ocean at one point in its history.
Pretty cool. We have one more question I wanted to get to. This one came in right before the broadcast, actually, asking, we've all seen this great blurry picture of Ceres, and we're looking forward to what's there. Is that orange color an illusion, or is that real? Is it just you think it'll be as gray as Vesta, or are there other materials there?
Well, I'd caution you to think that Vesta isn't actually gray. Most of the images that you saw from Dawn, those are black and white images. There's color information, but we don't, our cameras, when we take them out with spacecraft, they don't work exactly the way your camera in your iPhone, for instance, does. So what it does is it reads out brightness and darkness information, and then other things like filters. We actually put a filter, a red filter, a green filter, a blue filter, something like that, in front of, basically through which the light's going to pass to hit the CCD. So Vesta's not actually gray. It's kind of a, it's a little bit reddish colored asteroid, but you're not getting true color in most of those images. So the image that you're seeing here, the one that I was showing of Ceres, is a kind of real color image. It's not completely true. It's not every visible spectrum wavelength. It's a few select ones. This one is a composite image of visible light wavelength light, but not the full range. So it's not exactly what you would see if you flew right up to Ceres.
Cool. I would like Julie to get a chance to introduce herself. I know you've been posted a comment in the back channel, so why don't you introduce yourself and talk a little bit about your work?
So yeah, hi everybody. It's very nice to be part of this hangout, and thanks Brittany and Nicole for inviting me. So I am also a scientist in touch with the Dawn project, and I'm especially interested in Ceres. Originally I am an IC satellite specialist, but then I got to work with about Ceres, and there is something very formidable with Ceres, is that, as Brittany said, I mean, in terms of size and in terms of density, we can tell that there is ice on this object. But the big difference between Ceres and other icy bodies is that it's much closer to the sun, it's much warmer, so it means that its internal evolution, the prospect for the ice to melt, for liquid water to form a deep ocean for some period of time, and maybe for life to develop, is very strong in the case of Ceres. And something very interesting is that when the Dawn mission was proposed, I mean, if you can find the original proposal on the internet. You can see that 10 years ago or 15 years ago, Ceres was seen as a building block, a remnant protoplanet, very old. If you get to Ceres, you will find information about the very early solar system. And in fact, we now have a better understanding of Ceres' evolution, and we understand that actually it's a body that has been subject to a lot of evolution. Because we know that Europa, is a very interesting body because of its astrobiology potential. Enceladus is another icy body with an ocean and strong astrobiological potential, and Ceres should be in the same category.
Cool, cool. Yeah, I had no idea it would be so much similar to those icy worlds in a way.
Yeah, what's actually really exciting is that if you've been paying attention to the Cassini mission, you've probably seen a lot about Enceladus. What's cool is that Ceres is actually twice the size of Enceladus. Enceladus, if it was moved to the asteroid belt, would only be the 4th largest asteroid. So Ceres is not only special because of being so close to the sun, but it's also much bigger, much more energy, much more rock and water reactions that could have happened early in its history. And that's actually why we think it's so special, is that it's actually arguably more interesting than some of these icy satellites we've been to.
So Dean Callahan wants to know, when do we get a picture of Ceres better than the Hubble picture?
Late 2014, probably, or early 2015.
Okay.
We haven't really, because of the way the Dawn mission actually works. You've got the ion engine providing propulsion the entire duration of the mission. So what happens is that it depends on how long we're thrusting, how long that engine is turned on. That affects when we will actually arrive there. So we're not quite sure exactly what the trajectory is going to be. We should arrive at Ceres somewhere in the March to April timeframe. So it's a little bit different than most missions where we launch on this date and it will arrive on this date. So the same thing happened with Vesta, where our trajectory and how long we're thrusting actually affects when we get there. So the answer to that question should be kind of late 2015, December-ish timeframe, or around late 2014 or early 2015.
Okay. So what else do we know about Ceres so far, and how have we studied it before actually visiting the asteroid?
So maybe I can answer about my preferred things about Ceres that we've learned recently. I mean, so thanks to observations from the Earth, carbonates have been found on Ceres. And it's quite a unique thing. First, it's a robust determination. It's one of the things that we can trust the interpretation of the spectroscopic data. And it's quite unique. I mean, there are only 3 bodies on which carbonates have been detected: Earth, Mars, and Ceres. So that tells us something big, is that there is a process that involves water, that involves heat, and that led to the formation of these carbonates. And the one process on Earth that is well known, where an environment where you find these carbonates on Earth, is in hydrothermal fields, like the Lost City fields, for example. Where you have this luxuriant fauna, all types, very large diversity of animals. This is where you find carbonates, for example. So to me, it's extremely exciting. It tells us a lot about the evolution of Ceres.
Yeah, so Jill is talking about spectroscopic data. So I was going to show, I've got an image. One of the first ways that we thought Ceres was really interesting was, as she said, using spectroscopy. So if you look at the image that I'm going to show is the 2 spectrum, one of Ceres and one of Pallas. So Nicole, if you wouldn't mind throwing that on the screen. So what you're looking at here is a measure of reflected light that's coming from Ceres. So when we talk about spectroscopy, essentially what's happening is light is bouncing off the surface of Ceres and it's being returned back, reflected back towards the Earth. When you use a spectrometer, you can basically add up the strength of the reflection over the individual wavelengths of light. So that's what this is showing. This is showing a region from the visible to the near infrared. And if you look down kind of at the bottom, there's a guide. It says 0.3 all the way to 3.6. Those are wavelengths of light, so the actual wavelength of light in microns or micrometers. So if you look over at the little number, there's a number that says 3.0. If you look up above that, you'll notice that Ceres and Pallas, their spectrums are doing 2 different things. In both cases, what's happening here is that's a spectrum that's telling you water has been involved in the creation of the materials on the surface. If you look at Pallas's, it's kind of making a V like this. It's kind of making a steep arm. So that steep arm is actually telling us, so yeah, actually I'll do it this way. That steep arm is actually telling us that that's water of hydration, which means that there's little OH molecules tied up in the surface materials on Pallas. It tells you water was there at one point in time. It might still be buried deep below, but it's not really a part of the materials right now. If you actually look at Ceres 3 micron spectrum, you'll notice it looks kind of like a U. So that was actually the first indication that Ceres was totally different from anything else in the solar system. If you look at a pure spectrum of water, it looks a little bit more like this. In that 3-micron region. It's not perfectly like Ceres. Ceres is much more flat and broad, kind of like this. It's got some interesting features. And that little dip kind of out to the side over by 3.3, that kind of, there's a, you know, if you, so there's a one at 3, and then it kind of has an arm that does this over at 3.3. So if you look at that, that place is actually what Julie was talking about. It's actually detection of kind of carbonates that are involved in the surface materials on Ceres. So what that tells us is that there's actually water kind of bound, making a clay almost, on the surface of Ceres. One of the things you've probably been paying attention to is the Curiosity rover. It's been talking a lot about water minerals on the surface of Mars, carbonates. Oh, it's so exciting. Well, this is all literally bathing the surface of Ceres. So it's covered in these materials. And so it's a way for us to actually add that up, that Ceres, okay, so far we've got that its mass and size is telling us it's made of like half water. And then its spectrum is telling us, hey, there's a lot of material here that involves water all over the surface of Ceres. Now, it's not water ice. That's what makes it so different. So we're kind of in a situation with Ceres where you could say, you know, don't judge a book by its cover, or don't judge Ceres just by its surface composition. That it's just because we don't see water ice right there doesn't mean it's not very close. So we think this actually means is that impacts and activity on Ceres' surface has created a layer of material that's a mixture of some of its original material and material falling down in the asteroid over the course of 4.5 billion years of solar system evolution that's creating this mixture of water-rich materials that we find on uninhabited planets like the Earth and on potentially habitable Mars. So it's a unique thing that Ceres has going for it.
So the blue in the image, Charles Bell is asking about the Hubble image, that blue is not some kind of atmosphere or water on the surface currently.
Nope, we don't have the resolution to actually be able to see that. Now, that said, there was actually one detection of OH emission near the poles of Ceres. It's not been repeated. We haven't been able to repeat that detection, but that was made in, I believe in the 90s. But they basically think that there might be water evaporating from Ceres, and it wouldn't be very surprising actually if we went there and found it. So Ceres, what's kind of cool about it is that it's a perfect shape. It's perfectly oblate, and this is some of the work actually that Julie's done and that Julie and I have kind of worked on. Is what can you tell about the inside of a planet based on its shape, based on its surface materials? And so one of the things that we've been able to do is to look at, you know, I just showed a spectrum of Ceres and Pallas. Well, then what happens when we couple in their shapes as part of that? And that kind of gives us that history. So we can't see water ice directly. You know, the smallest thing we can see on Ceres right now is probably about 25 to 50 kilometers. So that's really, really huge. It'd have to be a giant chunk of ice. What you're looking at in those images is the fact that, you know, Hubble has great resolution, but you're actually getting little pixel effects. That's why it kind of looks, you know, a little bit of gray and a little bit of blue, and that's actually pixel effects. But when we get to you know, what we can see in those images is the fact that Ceres isn't all one color. There's actually bright spots and dark spots. And that's really exciting because in most asteroids, you don't really see that. It's one color pretty much everywhere. And that's important because it's another indication that maybe Ceres is doing something actively, turning over its ice shell or mixing materials on the surface, or that impact events are having a big effect on its surface composition and the surface of the asteroid. So it's very compelling in terms of what we might see when we actually get there.
So I'd like to add something regarding the detection of water. The Herschel Observatory, the team has reported a detection of something very special at Ceres, and it's work that is being published, so I can't give you everything, but stay tuned. I think it's going to be unexpected and amazing.
Oh, so that's like a tantalizing look for this to come soon.
Yeah, it comes very soon, and Herschel has the capability to detect water molecules around bodies.
Yeah, so lots of exciting new things.
We have questions about Dawn's visit to Ceres. How long will Dawn stay at Ceres? And you were speaking about shape just before. Will Dawn have any instruments that will be able to measure exactly how round or spherical Ceres is?
Yeah, that's a really good question. So Dawn will be at Ceres right now. The nominal mission's about 5 months. The thing about it is that Dawn has had some difficulties, and so we'll probably be staying at Ceres. Like we're not going to leave and go somewhere else. But what that means is that we'll probably get more time, hopefully, at Ceres. Now, there's all kinds of factors that go into that, but the initial mission plan is about 5 months there. But if you remember what happened with Vesta, we had about 9 months planned at Vesta, and then we ended up staying longer, a little over a year. So Ceres, no decisions have been made about what Dawn will do, but the nominal mission plan is 5 months at Ceres, and if the spacecraft is still working, we'll still be working on it too. Most missions that are still successful and still operating end up continuing, so it's probable that we'll get more and more observations at Ceres. That all depends on lots of decisions, so none of that's actually been made for now. So for now, we know we have 5 months and 2 different orbital phases, a high altitude orbit, well actually I guess 3, there's a survey orbit, and then a high altitude mapping orbit just like at Vesta, a little further away than it was at Vesta, and then a little bit of a lower orbit, and that one's also a little higher than it was at Vesta. But we're hoping that we'll have some more time in a working spacecraft at the end of that nominal mission so that we can extend it and be able to do some more science. That's of course getting ahead of oneself, so for now we're just planning for that nominal mission. But you were saying, are we going to be able to measure Ceres shape? Yes, of course we will. One of the things we can do when we're starting to come in is we'll actually be taking observations of Ceres, mostly using the cameras and then of course with the spectrometers. But we use those cameras and lots of rotational images to be able to get a great shape model. You know that you've probably seen the images, and if you haven't, you should check them out, of the shape models of Vesta. Those are all made using the cameras on board Dawn. So we'll get just as good a shape model probably for Ceres, and that'll be constructed over the first part of the mission. So we'll get lots of opportunity to see that. And that's really important because we'll get a really accurate measurement of its mass as well. Right now, we know how much Ceres weighs, if you want to put it that way, by its interactions with other asteroids. So it goes by Mars or it goes by another asteroid, and it kind of tugs on them a little bit. And based on how much it tugs those things out of orbit, that's how we know how massive Ceres is. However, when we get there with the spacecraft, we'll actually be able to look at how Dawn is flying and record that data, and that's actually part of the gravity science. So when you think about gravity science, there isn't a gravity detector. You don't like send gravitons out and try to get the weight of the planet. But when we get there, we'll actually be able to let Ceres let Ceres tug the spacecraft around. And how that happens is how we know the mass and the mass distribution inside the asteroid. That's really cool because that'll be actually how we can tell how much ice is there. Where is it located? The way that you do that is based on density contrast. So if I'm holding a piece of iron and a glass of water, those are very different densities. And so the spacecraft, based on the orbit of the spacecraft, we can actually tell where the water is inside of Ceres. Now, we won't be able to tell if there's an ocean or not. We'll have maybe some indirect evidence, but we will be able to tell that there's ice or an ice water layer there.
Cool. So the spacecraft itself is kind of the test particle in that gravity when you're measuring the mass and the gravity.
Basically, you can kind of think of it as Ceres is tugging it around. So.
Yeah. We have a question about the origin, I think, of Ceres from Rob Kroll. Can Ceres be one of the protoplanets to survive to present time? And I'm not sure what this is. The famous phaeton theory. I don't know if you've heard of that. Maybe you can say a little something about the origin of Ceres.
Yeah, so what we know based on, unless Julie, did you want to?
Yeah, I don't know what the phaeton theory is. Sorry, I can talk about the origin.
Yeah.
Sure.
Yeah. So because Ceres is this huge body full of water, and carbonate tells us that there are organics in the body and so on. People have been wondering if it's a body that could come from the outer solar system, and whether Ceres was formed in situ in the main belt or was formed in the outer, very far away in the outer solar system, and then migrated toward the inner solar system. It holds the key to a lot of things. It holds the key to better understanding how the current architecture of the solar system came to be, if you want. Because we don't really understand, or we don't have a definitive answer about the origin of water and organics in the inner solar system. So if Ceres formed very far and migrated and was captured closer to the sun, it tells us that there are a lot of volatiles, maybe all the volatiles that we find in the inner solar system, on Earth, on Mars, and so on, came from the outer solar system. So that's very important. And there are ways we've done to answer the question of where Ceres comes from, using the chemistry as a key source of observations. As Brittany showed, I mean, with spectra, you get constraints on the chemistry. There is another instrument on Dawn, which is a gamma ray and neutron spectrometer, which basically looks at how elements and minerals in Ceres react with particles hitting its surface, especially cosmic rays, gamma rays, and so on, and how these elements that are ejected in consequences of these collisions are going to give us information about the composition of Ceres. So it's especially the chemistry that is important in that case, and we hope to find markers of origin on Ceres' surface.
Yeah, and so that's kind of the question of where Ceres formed, but there's another question as to when it formed. So early on, very early ideas were that it took a really long time to build some of these planets. But the more that we find out about our solar system and about other solar systems, the more it seems that objects like Ceres and like the Earth grew very, very quickly. So one of the things that's really interesting is that we can test that using Ceres shape. So that's one of the ways that we've actually been able to figure out that Ceres is a surviving protoplanet, that it's something that formed early in the solar system. So I'm going to show you another image, which is, it's a little bit complicated, but I'll walk you through it. So let me actually go ahead and put that up.
Oh, is it the icy formation one?
Yeah, I'll go ahead and put that up because then
Okay.
I can point out all the features.
Sounds good.
So let's go ahead and take a look at this image. So this image is can you guys see that? Okay.
Yeah,
So
I have it focused.
Can you see my cursor?
Yes, I can see a little cross.
Great. So what we're looking at here is kind of a hodgepodge, but we were talking about, where is volatiles and where are these icy bodies in the solar system. These are all objects that are in the main asteroid belt. So most of them are between 2.5 and about 3.5 astronomical units. So 2.5 to 3.5 times the distance of the Earth from the Sun is where they're located in the solar system. So if you look up here, I've got there's a box up here. I'm circling it real slowly. It says 133P Elst Pizarro, P 2005 U1 Reed, and 1999 RE70. So these are main belt comets. They're actually little pieces of an asteroid that was not quite Ceres size, about half Ceres size, when it was originally formed. And then it broke up. And what's left are water-rich objects and another type of object called a C-type asteroid, which we think might actually be water-bearing as well. But it's kind of a question. So we've got these little asteroids that are activated that have actual comet-like trails that tell us we think that there's water ice down there. If you look below that, you'll notice Ceres in that big, round, gorgeous shape. And if you look across the image over here, we see 2 Pallas. Pallas is the second largest asteroid by size, third by mass. And that's the one I was showing you the spectrum of that kind of had that V shape, the water of hydration. So what we're actually been able to do is to model the shapes of these asteroids, of Pallas and Ceres, and say something about when they formed. So basically, the fact that Ceres is so round, just like you see in this Hubble image, tells us that it almost certainly had to form very early in the solar system. The reason for that is because these asteroids are so small, or, well, they're not so small, they're actually huge. Ceres is the size of about the state of Texas, which is a pretty sizable object. So if Ceres formed too late in the solar system, we wouldn't expect it to end up round. It can get round easier than any other of the asteroids, but it wouldn't be so round if it didn't happen early on. And it's basically shown here in this image, is that when they kind of form out of this rocky ice mixture, and they can take any kind of an evolutionary path. So what we think happens is that as they heat up from the decay of radiogenic nuclides, so radioactive materials just like we find inside the Earth, there were short-lived ones that only happened early in the solar system. And so you went from something like this, that was an ice-rock mixture, to something more like this, where this white layer here is an ice layer, the brown layer is a layer of hydrated material, and the green layer is a layer of dry material, so material that hasn't necessarily reacted with as much water. And then we think that Ceres could have taken, depending on when it formed, a number of different evolutionary paths, most of which lead to this big, round, beautiful object. So we can use Hubble Space Telescope observations of how big Ceres is and how flat it is. Basically, how flat it is, so how fat it is across its equator and how flat it is across its poles. And if you look at that, that actually tells you what its interior is doing. So based on that, this model is actually by Julie. So what it's kind of telling you is that Ceres went through this pathway from here, where it was an ice-rock mixture, through to being kind of a mud layer with ice, and then into these other more thermally processed layers. And what's cool about this is that when we get to Ceres with Dawn, we'll be able to tell the gravitational signature of whether it has just an ice layer, a wet silicate layer, and a dry layer versus whether it might even have formed a metallic core. And that will actually tell us exactly when it formed, whether it formed in the first million years of the solar system or within about the first 5 million years of the solar system. So in that way, the gravity detection is actually a way of kind of slicing Ceres in half and then also taking it back in time to figure out when it formed. And we think that Ceres is very special. As you can see, it's a different case over here for Pallas, where we think what we've got left is kind of a layer of water-rich but mostly silicate material where most of the ice is gone. So we can actually use the gravity detection in concert with these other instruments to be able to tell us about the history of Ceres. So that's what we're looking forward to doing, because we can actually time its exact formation in the solar system. We're able to do that with Vesta because of Vesta's differentiation, because of its surface. We can confirm that it is a very, very early object that formed in the solar system, actually even before any of the large planets were fully formed. So Ceres is probably very much like that, but using the gravity science on Dawn, we'll be able to tell exactly when it was born.
Very cool. So we have a couple questions coming from Twitter. Whitney, did you want to just talk about the formation question?
Sure thing.
Okay.
So one question that came through is Ceres in resonance with a bigger body? Did it migrate during the formation of the solar system, do you think? That's from Twitter.
So yeah, so I can comment on that. So two questions here. So first, Ceres is not in resonance with a bigger body, but it's been suggested that you have a bunch of small asteroids that are on the same exact orbit as Ceres. So in some form, they are in resonance with Ceres, and there are about 35 to like 45 of these objects predicted so far. And so that could be something that Dawn could see on its way during the approach phase to Ceres. Regarding the migration from the outer solar system, it's a little bit difficult to prove from a dynamical point of view. I mean, many people have worked on this topic, and I think they predict the probability of capture of about, I think, less than 10%. The migration part is not so much the problem. The problem is more about, how do you capture an object that is so massive? How do you break, if you want, the course of an object that is so massive? But it's not a zero probability, so, I mean, we'll see.
Thank you very much.
Sure.
And Julie, I think you also wanted to talk some about the astrobiological potential of Ceres.
Yeah. So I mentioned earlier that big thing with Ceres. I mean, we talk about it having an ocean. We talked about it having ice, and maybe, I mean, there are carbonates on the surface. So maybe, we can speculate that Ceres could be similar to other icy satellites for which a deep ocean, possibly inhabited, has been suggested. Can you please put up my slide about the comparison between Earth, Europa, and Ceres?
Oh, sure. I can do that.
So, yeah, the second one.
Next one. This one?
Yeah.
The chart. Okay.
So I can't see it so well.
So if you click on the little window on the bottom, it'll show up on the big screen for you.
Okay. Okay, I don't see that, but I don't want to delay you. I'm just going to describe it. So it's a chart that basically in the first column lists all the attributes that that makes a body habitable. And I have tried to quantify when possible, or at least qualify what we think is going on at Ceres compared, again, what we think is going on at Earth and at Europa. And Europa is this very, huge astrobiological target. So, so I don't see the slide, but basically what I've done is looked at, does this body has a deep ocean? And it's been suggested from geophysical modeling that indeed Ceres could have preserved, at least at the equator where the surface is warmer, it could have preserved a liquid layer that would be a few kilometers thick. That this layer could have salts. I have tried to quantify the heat budget of Ceres, and the heat is very significant at Ceres. So at Europa, we know that the heat source is primarily from the core, from radiogenic heating, and also from tidal heating, from the consequence of Europa's interaction with Jupiter. So Ceres is not in resonance, as we just said, is not in resonance with the Sun or any other body, but it's very close to the Sun, and basically the Sun is the main heat source for Ceres, as it is for Earth. I mean, it's one of the key heat sources for Earth. So the surface temperature of Ceres is so warm that its ice can deform very easily, and this drives likely the internal processes and what we call convection, the motion of material within the icy shell. And that motion of material is very important because what it can do is bring material deep in the interior of Ceres, like for example from the ocean, and bring it to the surface of Ceres. So let's say you have very elaborate organic molecule in Ceres' ocean. There is some prospect that convective motion within the ice shell could bring that material to the surface of Ceres. And then I looked at other things, like, for example, is there a prospect for hydrothermal activity, like we find on Earth, and has been suggested for Europa. And, you know, the presence of carbonates on Ceres, as mentioned earlier, is kind of evidence for hydrothermal activity in the past of Ceres. There are other information that we can think of, but these three aspects, you know, the chemistry, hydrothermal activity, the heat source, and the prospect for convection within the ice shell are the key ones that make us think that Ceres could have been habitable at least at some point in its history.
So we have a question asking if it's okay to make these slides available for download after the show, Julie.
Oh, no problem.
Brittany. Okay,
Right.
I can post them as images in the Google Plus event right after the show, so we'll post them there.
Yep, go right
Awesome.
ahead.
And this also answers a question, oh gosh, I need to find it. Charles Bell asked if there's been a calculated range of surface temperatures for Ceres, and so that's right here. It says 130 to 200 Kelvin. Below the thermal skin, what was the thermal skin?
So, oh, Brittany, can you comment on this? I think you can explain very
Yeah,
well.
sure. So basically, there is a layer on the outside of any asteroid or any object, basically, that the surface, there's a layer basically that changes temperature wildly depending on whether it's lit up or whether it's in shadow. So that's what we call the thermal skin. So when we say surface temperature, that's basically the stable temperature, the most stable temperature. So it's a few centimeters underneath the surface. So effectively it's the surface temperature. It's basically how deep a thermal wave would penetrate into the object. So it's kind of like you know, if it's a hot day, it's a hot day out, and then the sun sets. The very surface, sometimes of a material that you're standing on, you still might feel some of the warmth coming back up from down below. So it's that kind of like an insulated layer kind of thing.
Okay, cool.
It's a way to think about it. It's not perfectly correct, but that's a way to think about it.
We had another. Oh, go ahead. Go ahead if you wanted to.
Oh, I was just going to mention what I think is really fun about Ceres is that despite, you know, we kind of debate whether or not it could still be going on, whether it could still be getting going, but we know that it almost certainly, if it does turn out to be icy, it had to have had an ocean at some point in time. Whether it still exists now is a big question. It's too bad we don't have a magnetometer on that mission, because if we did, we'd be able to tell if it had one today, but that's just how it goes with these things. But what I think is really exciting is that now I study Europa. Europa is my thing that I work on the most, at least right now, and because I'm really interested in the search for life beyond Earth. And the one thing I will say is that what's great about Ceres is that this surface, you know, it's not a difficult environment to investigate. We're not going to get baked out on the surface by radiation like you would at Jupiter. It's relatively warm compared to other places in the solar system. So if we think about you know, the future of landed missions for people, for rovers or something, why not go to Ceres? I mean, you've got all this water-rich material that's right there on the surface. Just really interesting chemistry that could be going on. Even if life never got started on Ceres, it could tell us so much about early solar system and evolutionary chemistry on planets. Just amazing place. You have probably a rock and dust layer, so it's not as easy as, you know, you're not going to be able to drill into it as easily as you could on Europa, for instance. But if you wanted to go, you know, rove around and do some really cool chemistry and maybe find some exposed ice, you know, here and there, maybe in an impact basin, hopefully we'll be able to tell you that with Dawn. I think that's a really compelling reason to think about Ceres. And it's funny because we have such a big planet bias. We have such a bias for looking for things that look exactly like us. And in this, you know, kind of special place in the solar system, we've got a very unique object that might be telling us a lot about what we don't know about building a habitable planet and maybe a launching point for getting to the outer solar system. You know, it's got a small gravity well. It's going to be easier to land on than Mars. right? So things like that I think are really kind of cool as we start to think about the future of manned exploration, even beyond robotic exploration. I think it's a cool destination to think of in terms of that.
This is great. I want my next vacation to be on Ceres now. You sold me.
Good.
Me too. Me too. Me too.
We're all going. Awesome. Yeah, I mean, Ceres has, such a storied history being a planet and then being an asteroid and now being a dwarf planet as well. So it's really great to see it coming back into the limelight with Dawn visiting it so soon.
Yep.
There was another question that I think came from Twitter about the brightish white spots in that Hubble image everyone loves referencing.
Yeah.
If that is some kind of crater, and if that is digging up older material from beneath the surface, that could be studied.
It's a pretty good chance that that's what that is. So the white color, that just depends on the filter. It just means that it was bright here. So actually, Ceres is a kind of carbonaceous asteroid, which means that it's actually really dark. So the actual color of Ceres is a lot closer to asphalt than it is to white. So it's actually a really dark asteroid. It has an albedo of around 10%. So it reflects 10% of the light that hits it, right? So that's way, way, way darker. So Vesta, for instance, is 40 to 50%. So it's actually really dark. So when you see a bright white spot in those images, it's not super bright white, but the fact that you're seeing a different color really tells us something. And when we look at images of Ceres in all different wavelengths, in the UV, in the visible, not so much in the IR, but when you see those, actually a little bit in the IR too, we see these kind of round circular spots. And what we don't know is what they are. They could be impact basins. They could be, maybe they're big, maybe they're chaos terrain like there is on Europa. We don't know. What's kind of interesting is that if you look at that picture of Vesta, there was a giant impact basin. We can actually see, we could see Rhea Silvia from a distance. We could see it with Hubble. We could see bigger basins that we thought were impact basins. We think we see them on Pallas, but we can't see any on Ceres. It's just perfectly round, down to 25 kilometers. Now, that doesn't mean that Ceres hasn't been hit by something that's bigger than 25 kilometers. It just means that whatever's going on Ceres has totally erased that, at least the topographic signature. So that's another reason that we think Ceres is icy. So what that may be telling us is, maybe that's the center of an impact structure, and maybe that's a really cool place where the chemistry is going to be different when we get there with Dawn. And it depends, in some wavelengths, the spots on Ceres are dark. Some wavelengths, the spots on Ceres are bright. And none of the spots are the same in every wavelength. So spots in different areas on the surface, there's really no surface feature on Ceres that's really been detected because it's different in every wavelength. It's super exciting. We're going to learn so much when we get there. We don't really know why it's flat. If you want to go back to that spectrum I showed, one of the things that's really puzzling about the carbonaceous asteroids, so generically the C-type, the B-type, the G-type asteroids, these are terminology that astronomers use to describe these asteroids. If you'll notice, there's kind of almost a flat line from 0.6 all the way across to 2.7. In Pallas's case, there's just a little bit of a dipping line. And we don't know why that is. When we look at Vesta, we see these deep absorption bands that tell us that its surface is covered in volcanics, covered in basalts. So those spectral features tell us that Ceres is kind of special, and there's a whole class of asteroids that are very similar in many ways to Ceres spectrally. They're different, but they've got that kind of flat visible infrared spectrum. And so we're really looking forward to figuring out what that means. So when we go to Ceres, what we're not only going to do is unlock a totally unique object in the solar system. It's actually because of some of its similarities to other smaller asteroids. It's actually going to tell us what these asteroids were like early in the solar system history, what created all of that dark material out there, what that dark material might be. So it actually is kind of like, Ceres is like the gatekeeper to the history of water in the middle solar system. And really, I think it's going to be very compelling when we get there and can figure out what all these what people have called boring spectra are actually telling us. So it may be ironic that the most boring spectrum in the solar system might actually be the most interesting. One of the ideas that's been kicked around is whether that's actually just a whole mixture of salts. So when we get to Ceres, might we see big circular impact basins with salt rings or something like that? That might be an indication that there was active water processing. Maybe that's why we can't see spectral features on Ceres with our ground-based telescope. So we don't know yet. It's going to be really exciting to see.
So there's a question again about this surface from Twitter as well. I've read that Ceres' ice is buried under non-ice material. How thick do we think that covering of a non-ice is?
So I can comment on that. So models have been done that suggest that the water would be buried below maybe 10, 20 meters.
Okay.
And it's very difficult to control. I'm sorry about the background noise. Do you hear it much?
A little bit. That's fine. We know you're at a conference.
Sorry. So yeah, so the water could be relatively close to the surface. But that's for the equator. At the poles, there is a great chance that water could be on the surface because there is what we call cold traps. That is areas that can remain very cold, and we have that. We found some on the moon, for example, where there are shadowed areas, if you want, where water can remain on the surface for extended period of time. And we've been working a little bit to predict where these cold traps are located. And something sure is that there is an instrument on the Dawn spacecraft. It's called a neutron spectrometer that can find water, provided that it's like within 1 meter from the surface.
Okay. Awesome, thanks. I want to screen share an image posted in the comments by Jason H. And he looks like he's put together a little movie using Hubble images showing Ceres in rotation. So I haven't seen that before, so I thought I would show that. So can you all see that?
Yeah.
The little spot moving across. So,
yeah.
So yeah, that's a link to that is on the event page in the comments. So thank you for that. Thank you for that, Jason H. Show that real quick. Also, I have to share a little pun. Hugo Burnham says there's a whole series of stories to tell about Ceres. So thank you for that.
Yeah, well, actually, that's really true. So we're actually going to have another hangout like this to talk about Ceres in a couple weeks on September 5th. So we'll have a new group of scientists and tell a little bit more about it, what people are looking forward to. So yeah, nice pun.
Gets right in.
Series.
So we are coming up on an hour, so I wanted to give Brittany and Julie each a chance to maybe give us their last thoughts about Ceres, what we know about it now, and what they're excited to see when Dawn gets there. So Brittany, do you want to start?
Sure. Yeah. I just kind of wanted to just share my excitement about getting a chance to see another icy world in the solar system, and I'm privileged to have been a part of Dawn since I was a grad student. I've worked on this project in a lot of different ways, and I can't wait to get to Ceres. There were a lot of people that were very compelled by Vesta. Vesta, we have meteorites back from, and we hold pieces in our hand, and so the spectrum, that was one of the first solar system objects that we took spectroscopy of and could actually detect what was on the surface. So Vesta, in many ways, has been kind of the low-hanging fruit, but I think what we're going to find out is that when we dig a little deeper, Ceres is this special place too. And I like to say that when we got to Vesta, we really confirmed things we thought we knew. So it was idea affirming. And I think when we get to Ceres, it's just going to be absolutely a game changer, a new window into the solar system that we wouldn't have without going there. So it's just another reason why planetary exploration is so important. It's telling us about ourselves, our history, and it's developing new technologies and new understanding, new knowledge, and if it does nothing else than inspire us to get up in the morning and smile and have a better day, then I'm happy. And so I encourage everyone out there who's watching to just realize all the special things that planetary exploration does for us, and what an awesome time it's going to be when we get to Ceres.
Cool. Julie?
Awesome.
Yeah, I wanted to mention, can you show the last slide that I sent you?
Sure, yes. I like this one. Slowly coming. There it goes.
So 2015, and even starting in 2014, it's going to be a very exciting time because there are going to be 3 missions going to small bodies. There is a Rosetta mission going to a comet, and in 15 there are Dawn at Ceres and the New Horizon missions arriving at Pluto and Charon. And the special thing here is that Charon, so Pluto's satellite, it's about the same size as Ceres. It's about the same mass. But the big difference with respect to Ceres is that it's extremely cold. So here we'll have an opportunity to do comparative planetology, looking at objects that are very similar in many regards, but differ in other regards, and understand how the effect, especially of temperature, impacts the evolution of these bodies. So, 15 is going to be a great year for icy bodies.
That's excellent. I am excited to see all of them close up as well. Whitney, do you have any last message from the Dawn EPO team? Or
only that we're I don't know, beyond thrilled for 2015 and looking to develop some great materials that are going to help tell the story and help us access the story of the Dawn mission, and particularly our next phase here at Ceres. And Ceres is right on. We've got more stories to tell, and we hope you'll join us to hear them.
Excellent, excellent. So thank you so much, everybody, Brittany and Julie and Whitney, Judy, who's also running support for us in the background. Thank you so much for coming and sharing the story of Ceres with us here. This has been really great. And thank you for all the commenters for joining in, and your comments and your questions, and supporting planetary science, because it's amazing stuff that's going on out there. Yeah.
Yep.
Don't forget, you can still explore Vesta through asteroid mappers on CosmoQuest. So we're still looking for you guys to map the surface, mark the craters, mark boulders, get on in there. So at cosmoquest.org, there's a little image right up front that goes between the Moon, Vesta, and Mercury. And so go ahead and check out all those bodies and help us do the science. Help us figure out what's happening on the surfaces of these worlds. Vesta's a strange little world and really fun to map and check out. That, I think, is it for today's show. For the rest of the CosmoQuest schedule, you can look at cosmoquest.org/hangouts, tell you what the next hangout is. Tomorrow's Friday, so tomorrow will be the weekly space hangout at noon Pacific. Fraser Kane hosts a bunch of us rowdy scientists and science journalists as we talk about the week in space news. Sunday night is a virtual star party. Monday is Astronomy Cast. Fraser and Pamela Gay will record a live version of Astronomy Cast. And Wednesday is Learning Space. That is our education and outreach hangout, and so I'll be running that. So that's our usual weekly schedule. Thank you again for joining us, and we will see you next time. Bye. Hi, everyone. Welcome to the special CosmoQuest Dawn Hangout. We are going to be talking about the largest asteroid and also known as dwarf planet Ceres. I am Nicole Galucci. I am a postdoc with the CosmoQuest project, so I'll be checking your comments and running some tech while we do this hangout. And I have with me Brittany Schmidt. Hello. And Julie Castillo Rogez. Sorry. So these are our two scientists who will be talking about the science behind Ceres.
Julie, are you there?
Yes.
There seems to be a delay.
All right, we're almost up. We're here.
Yay! Julie, can
Hi, everyone. Welcome to the special CosmoQuest Dawn Hangout. We are going to be talking about the large...
Oh, sorry. Okay, so Whitney, the sound's coming through your speakers. Sorry, Julie, I muted you. You can unmute yourself again. Sorry, we're having a little bit of tech difficulties. We also have Whitney Cobb from the Dawn mission. She is behind the Twitter feed, and she will be helping us answer your questions. So what's the Twitter handle? It's at NASA_Dawn. Okay, so we can't hear you right now.
Yeah,
sorry.
there you go, yeah.
Awesome. So she'll be answering your questions on Twitter. Some other ways that you can comment, ask questions is using the Google event page. So if you're watching on the Google event page, we're watching those comments already. So we see lots of hellos from Indy, from Norway. So hi, everybody.
Awesome.
And also, yeah, also the YouTube page. If you're watching this on YouTube, you can use that comment thread as well, and we will see those. Brittany, do you want to go ahead and get us started talking about Ceres and what we know about that dwarf planet already?
Yeah, sure. So I'm excited that everyone could come and listen to this, and if you're watching this after the facts, thanks a lot for being interested. So I'm one of the scientists that's involved with the Dawn mission. I'm actually on the education and public outreach team, and I'm coming to you from Atlanta, Georgia, actually for the first time. So that's kind of exciting. And we thought we'd have a discussion today about Ceres because it's the next target for the Dawn mission. So in the past couple of months, even the last year or so, we've been telling you a lot of information about Vesta, which is the first target that Dawn visited, spent about a year orbiting Vesta and doing great science there. And so where Dawn is at right now is actually kind of halfway between those asteroids. We're looking for arrival at Ceres in actually very early 2015, somewhere around March 2015. And what we wanted to do was to share with you why we're so interested in Ceres, especially alongside Vesta that we've just departed from. So I'm excited to tell you about Ceres because I think of Ceres actually as a game changer in the solar system. So in many cases, we visit classes of objects. We visit asteroids, we visit icy satellites, we visit gas giant planets, we've visited the terrestrial planets time and time again. What's really interesting about Ceres is that Ceres is arguably the only one of its kind. It's the innermost potentially icy body, at least a major body. Ceres was discovered in the 1800s, actually, by German astronomers, and was originally designated a planet. It was actually so large. It was exactly where we expected it to be from the Titius-Bode law, which is an observational law. So people went looking for this missing planet. What they ended up finding was Ceres. We now know Ceres is the largest asteroid, or the earliest discovered dwarf planet, if you want to think about it that way. But Ceres is a really, really exciting object. And the reason for that is because of what we know and because of what's so surprising about it. So we think about asteroids, we think about dry objects, we think about little pieces of rock floating in space, and it turns out that Ceres is not like that at all. So I've got an image here actually showing Ceres alongside the other asteroids that we've visited with spacecraft. And just to give you kind of a sense, if Nicole throw that up. So this is an image of Ceres. And Ceres is that big round one in the middle. Ceres is almost 1,000 kilometers across. So if you're thinking about an asteroid, you're usually thinking about the things I'm showing to the right-hand side of that image. So if you look there, you've got Itokawa, you've got Matilda, you've got these asteroids, Anne Frank, that we've visited with spacecraft. And that's their actual size, with the exception actually of Itokawa. So Itokawa is the kind of the third one on the right-hand side, kind of little bent, kind of dusty-looking one. And Itokawa, that's actually about 5 times its actual size, that little tiny box that I'm showing right there. So that should give you kind of a perspective on why Ceres is so special. But if you look at Ceres more carefully, what you'll notice is that it's also totally a different shape than what you see, even with Vesta, even with this giant planet-sized asteroid that's the size of Arizona, right? That's how big Vesta is. And we saw it was basically round. It had all of these planetary-type processes going on at its surface. But even if you look at Vesta, you'll notice that it even doesn't look as round as Ceres. So that's the first real indication that we had from direct imaging that Ceres was so special. We knew other things about Ceres beforehand, but basically it's the combination of this shape, its size, and its total mass that actually tells us that Ceres is incredibly low density, despite being almost 1/3 of the mass of the asteroid belt. What that tells us is that underneath this kind of dusty, dirty, clay-type surface, we think that Ceres might actually be icy. So if you want to think about it, it's a little bit like a Europa or an Enceladus with a dusty layer on the outside. And it's the only object that we know of in the whole solar system that's like that.
Brittany, we have a question, I think, relating to that from Sylvan Westby. Has Dawn crossed the frost line?
Well, so that's actually a really interesting question. So the frost line, or the ice line, or you may have heard the snow line, is kind of a concept that astronomers and planetary scientists use to describe a concept that somewhere in the early solar system, there was a point at which water ice became stable, where when you're building a planet, instead of just sweeping up rocks, like mostly what the Earth and Mercury and Mars and Venus, mostly what they swept up to build themselves was solid material in the form of rock. Well, there's a certain position in the solar system where solids also start to include ice, where it got cold enough in the solar system for ice to start forming. And so basically at that point in time, you can start sweeping up rocks that are actually made of ice. And so we think that that's what's happened in the case of Ceres. So what's interesting is that as we learn about Ceres, if Ceres does in fact turn out to be icy underneath that dusty regolith, then that'll actually give us an idea of potentially where the ice line was in the early solar system. We don't actually know what that position was, and it probably changed in the history of the solar system as planets were migrating around and as the sun was actually becoming more and more energetic. So we're not quite sure exactly where that frost line was, and so if we can actually confirm that Ceres is icy at 2.7 AU, then that actually gives us an idea of where that frost line might have been in the early solar system. So it's a really good question. That's actually one of the reasons that we're so interested in going to see Ceres, is because of that implication for what water was doing in the inner solar system. That's of course important because water is important for us, and it's very important for Ceres, which may be made of ice and potentially have had an ocean at one point in its history.
Pretty cool. We have one more question I wanted to get to. This one came in right before the broadcast, actually, asking, we've all seen this great blurry picture of Ceres, and we're looking forward to what's there. Is that orange color an illusion, or is that real?